Wow, there's so many people. Yeah, thank you so much for coming to my talk. Hello, my name is Amanda Hinchman-Dominguez, and this is Crash Course on the Kotlin compiler. So, you want to get to know the Kotlin compiler. I did too. For me, it started when I was playing around with automated generative UI testing for Tornado FX and using AST parsing. This led me to help build out the Kotlin template system for Arameta, an open source library on making compiler plugins with less boilerplate. Oh, there was an animation. That's kind of fun. And most recently, I've lifted the hood for the Compose in a joint talk with Yossi Wolf on Hitchhiker's Guide to Jetpack Compose. And I've come to the same conclusions as the rest of you. Navigating the compiler is hard. And when there is documentation, it feels like it's kind of in bits and pieces. So I put together a gear kit in the hopes of giving people just enough information to get their hands dirty themselves on playing around with the Kotlin compiler. More backpacks, more dropping, I love that. So to learn more about the compiler in a short amount of time, today we're going to reverse engineer a few popular compiler plugins and pair it with a diagram of the Kotlin compiler to learn better about the internals and maybe exchange some notes in the end. We're about to go into a really, really long explanation, so. Okay, source code is submitted through the compiler to turn human-readable source code into machine-executable code which runs on whatever designated machine. This is accomplished with a few cycles of intermediary data generation and subsequent transformations of aforementioned data formats. If we were to grossly oversimplify the compiler, we can think of the compiler as basically doing two things, compiling and lowering. Compiling changes the existing data formats, and lowering simplifies those new data formats. When are plugins used? Well, you write plugins when existing language features for Kotlin isn't quite cut out for your needs, and maybe you need to stretch the limits of the current default behavior. Compiler plugins can intercept different phases of the Kotlin compiler by overriding default behavior to transform source code into targeted code. So when writing a compiler plugin, configurations must be chosen to run on the Kotlin compiler. So some of those things include deciding environments, so it might be CLI, analysis API, and so on, processor options, which plugins to hook into the compiler, and which front-end and back-end to choose from. So the Kotlin compiler has two front ends, K1 and K2, denoted with a prepended FE10 and FIR. Choosing a front end determines what information is sent to the backend for IR generation and subsequent target code generation. Both share similar stages in the beginning, only the FIR front end introduces an additional data format before sending it off to the backend. So what is most important to kind of get from this is that both front ends will send whatever formats of data, which will eventually be turned into IR, which is then sent into the backend for further processing. IR stands for intermediate representation, which will be covered later on. So the K1 front end sends the PSI descriptors and binding context to the backend. PSI stands for Programming Structure Interface. It's a layer in the IntelliJ platform to parse files and create syntactic and semantic code models. Binding context is a big map which contains information about all the program and paired to PSI. Descriptors, depending on the element types, like for example, a class descriptor, might hold context, scope, containing info, overrides, companion object, etc. In the case of the K1 front ends, all this information is sent to the backend to transform PSI into an IR, which is used for input for the backend. So suppose we have the following source code, fun2, which gives you 2, through the compiler. First, the Kotlin lexer will scan and break up the text into lexical tokens called KT tokens. For example, you have like the left parentheses and the right parentheses, and that might be denoted as KT single value, LPAR and RPAR, and then of course equals is EQ. White spaces are included as well, just not in this slide, because it's kind of noisy. Next is the abstract syntax tree, which constructs these lexical tokens into this tree and they have like a direct mapping to the text ranges in the source code. So this is what the AST might look like. Then the syntax analysis layers the PSI over the sets of expression nodes, which are then appended to the PSI tree. I feel like something happened really fast. Okay. IntelliJ has this super excellent plugin as an IDE plugin. It's called the PSI Viewer, which shows the relevant PSI trees corresponding to highlight the source code that's in your file. So at this stage, only the grammar is checked for syntactical correctness. We can say that the code looks right, but we can't say whether the code compiles or not. In resolution, semantic information is generated, giving resolved names for functions, variables, types, and it answers questions like, where does this function come from? And do these two strings refer to the same variable? In the case of K1, resolution is performed on the PSI tree to generate the descriptors in the binding context, where a PSI is the key to the map to the descriptors, and then the other information is used to infer upon itself later on in later stages. However, sending over the PSI in binding contexts like this led to performance issues in the compiler. With the old implementation of the front end, resolution was stored in this big map of maps, the binding context, so CPU cannot cache objects well enough. All the descriptors were lazy, and the compiler jumped between different parts of the code, which killed a number of JIT optimizations. To improve on compiler performance, JetBrains created the new K2 front-end compiler, denoted with the prepended FIR. So old structures were replaced with a new data structure called FIR, otherwise known as front-end intermediate representation. And this FIR is a semantic tree which represents the source code. Okay, so the FIR front end is the new front end for the Kotlin compiler, which replaces the existing one. It takes a raw PSI as input, produces raw FIR, which transforms in different stages during resolution, filling the tree with semantic information. So the resolved FIR is then transformed into IR, which becomes input for the backend. Okay, for the K2 front end, I'd like to look at a slightly more complex example and start at the same phase where both front ends kind of go before the differences start splitting off. Okay, so we have private val Kotlin files. It's a mutable list of 1, 2, 3. We're going to start at the PSI level again. Only we're going to move some of the backend off because there was a lot more for this one. I even took out the PSI white space because it would have been a lot longer otherwise, so we can read a little bit better. Instead of just generating the additional data to send the PSI off to the backend, we now compile this intermediary data format before the IR is created. So there is that front-end intermediate representation. FIR is a mutable tree built from the results of the parser, the generated PSI tree that we saw. In this raw form, you might notice that it kind of looks like the PSI, some of the elements that were in here. So for example, we have the mutable list, and we also have the Kotlin files, the var arg, and then way somewhere in there, there's value arguments. Yeah, so this is just kind of how it matches up. So after the raw FIR is built, we pass it to a number of processors, which resolves the code and represents different stages of the compiler pipeline. So these stages are applied to all of the files in a module in a bulk. So some of those things include resolving import directives, finding the class ID for supertypes and inheritors of sealed classes, resolving and inferring declaration visibility modifiers, resolving function contracts, inferring return types, and analyzing bodies of functions and properties. So the resolution stage for FIR front-end transforms the generated raw FIR in different stages, filling the tree with semantic information. For the FIR front-end, resolution already performs some desugaring for sampling further resolve. So for example, if statements might be replaced, or you can replace if statements for when, and transforming those for loops to while loops. So it used to be that we had to do all that in the back end, but now we move some of that to the front end with the FIR resolution. So we go through all that, And then there's also a last checker stage, which checks the FIR and reports different diagnostics, so this will include warnings and errors. And if there are errors, information is sent to the IDE plugin responsible for sending you that little red squiggly line. And compilation will stop since there's no need to send broken code to the backends. Granted that checkers returns no errors, the resolve FIR is then transformed to backend IR, which is input for the backends. Okay, this is done with the FIR to IR component. Okay, so we made it to the backend. There are, I guess, 4 backends. There's the JVM, JS native, and this one obscure experimental WASM. Don't ask me what it is, because I'll tell you, I don't know. So this excellent diagram, this is credit to Sletvanas Isakovas, what everyone must know about the new Kotlin K2 compiler. Highly recommend watching it in tandem with this talk as a supplement. What I want you to notice is that no matter which backend you go with, the IR generator and the optimizer is the same start for backend processing. Then the configuration that is selected will run the necessary generated code as needed, so then it just goes on from there. Okay, that said, we're going to select the JVM backend and continue with our current mutable list example. IR, or intermediate representation, is generated as another form of abstracted representation for CPU-level architecture. At this point, PSI and IR have symbol tables mapping their nodes to descriptors, so we have all this information already, and we can use it later on to continue inferring more information. So it's not super readable for us, but it is definitely way more readable for the compiler. Then analysis is performed on the IR, and this is responsible for creating things like control flow and call stacks. Then machine-dependent optimizations are performed on the IR. This is known as lowerings. I think the simplest way to think of this is if you have the IR equivalent of like 3 to the power of 2, it simplifies that operation to 3 times 3. It's oversimplified, but I think that just kind of helps understand what some of this does. So it simplifies operations, and it improves the quality and performance of produced machine code, especially around things like concurrency, and it also looks at resource and storage decisions. Okay, now the bytecode. The JVM bytecode is finally generated, and optimizations are performed on the bytecode, not shown in the screenshot. And in the case of the JVM backends, bytecode is generated and sent to the Java virtual machine to be executed. Okay, now that we're a little familiar with the Kotlin map, the Kotlin compiler map, we're ready to reverse engineer some compiler plugins. We're going to cover 2 scenarios, intercepting the front end and the back end of the compiler. Okay, front end interception, the front end example, will be covered with the SAM with receiver plugin, which is sitting in the Kotlin source code under the plugins file. It's called a SAM with receiver. So Hoyen is giving a talk this hour about SAM. I really wish I saw that talk, but we have the same hour, so it is what it is. Yeah, the SAM with receiver plugin makes the first parameter of the annotated Java single abstract method, otherwise known as SAM interface, receiver in Kotlin. The code in here shows the SAM with receiver 1 set to runtime, and it annotates the job interface class containing 1 function to execute. The manager class holds an empty method called doJob. It takes a function of the job type. This conversion only works when the SAM interface is passed as a Kotlin lambda, either as a SAM adapter or a SAM constructor. So our code shows a main function with manager doJob as a, it's like invocated 2 different ways. The first way is the SAM interface as the first invocation, and with the second invocation, it's done as an anonymous class. Without the plugin and the SAM1 receiver annotation not configured in, the SAM invocation fails for a couple reasons. This is not defined in this context, and it expected 2 parameters of type string and int, and there's also a type mismatch. If we add this plugin to our Gradle build and rebuild the project again, the results are now different. And of course, you have to add the annotation as well. So the results look different. Now, the first invocation as a SAM interface is resolved as compilable code, while the anonymous class invocation is now showing that it cannot compile. So kind of fun. Looking at the plugin itself, we can see the following packages. We have the CLI common K1, K2, and the CLI holds the code for the plugin itself. It has the logic for command line processor, component registrar, and compiler configurations. And the common one just shares like the same naming conventions. And then K1, K2, we're more interested in K2. That's what we're going to look at for this example. If you check the K2 build .gradle dependencies, you'll see a lot of hints for what the FIR compiler is made out of. You'll see that all the compiler modules lay in the compiler directory, and all the FIR-related modules are in compiler FIR directory. Okay, there's also, I put some definitions because I was like, what is this? There's cones. Those are all nodes of the FIR tree. Then you have the classes for the FIR type system under tree. For resolve, that has the resolution main logic. Checkers is intended for the diagnostics. And then there's also the entry point with the FIR compiler entry. I think there's like FIR analyzer facade test that might be worth playing around with, and you can just kind of see how deep down the rabbit hole you go. So, Kevin Most had an excellent talk back in KotlinConf 2018 called Writing Your First Kotlin Compiler Plugin. And this is a diagram that he had in his talk, and I thought it did a great job kind of breaking down what a compiler plugin looks like with like a Gradle wrapper on top. The top two has the plugin, which is like the API for Gradle, the sub-plugin, which is kind of like the interface between Kotlin and Gradle. And then you have the command line processor, the component registrar, and the extensions. Extensions are where you can extend phases of the Kotlin compiler and alter the default behavior within those extensions that you create. And those are what we are most interested in. Yeah, so you can see in the K2 that there's the FIR SAM with receiver convention registrar. We're going to take a look at that. And we can see that we pass in like a list of annotations, and when we configure the plugin, there's this FIR SAM with receiver convention transformer. So FIR extension registrar indicates we are working with the FIR data, and because it looks like we are intercepting FIR transformations, it's safe to say that we are working with K2 resolution. And if we step into the FIR SAM with receiver convention transformer, this is literally all the code for this entire plugin, which I think is fun. I love small libraries. I love small plugins. Always been a fan. So there's a lot going on here. We can see that annotations are being passed in. Then we have the get custom functional type for SAM conversion, and you can see that we're using cones to like look up certain types. And the highlighted code with the containing class symbol, so you take a look and you take a look at the FIR regular class symbol and you check to see if there are functions with that annotation that we're looking for. So this is how we are able to, at the resolution level, try to locate what some of the, like the SAM with receiver 1 might be located. So this is kind of where we're at. And then we have the run if. Once we have located that annotation, we're going to make sure that it matches the names that we're like checking in. So this is how we locate that registered SAM interface. Okay, here's where the real magic happens. If we have the parameter types, it takes the mapping for the cone types, and more importantly, we end up replacing the current functional type. So like whatever default there was, we intercept that and we create a new function type where it takes the registered return types of the value functions for that function. So you have your function, you're able to locate the properties within, and then it replaces the first argument as receiver type. So this is how it allows us to use this in its place. So like now it understands what this is. So what should have been context, it's now rewritten so that we just have it as a receiver type. And now you can kind of see how the compiler is able to alter that underlying behavior. Okay, we're going to go on to an example for the backends. The Compose compiler plugin, this is under the Android X project, totally different set of instructions, and also fun tidbit, I had to run both of them on 2 different computers because one only takes newer stuff and the other one, the Kotlin compiler, requires Java 6. So it was a pain. But yeah, okay, so we have this composable. For those who are not familiar with Jetpack Compose, it's a modern toolkit for building native UI. Compose is declarative, and it's also able to self-manage memory at runtime so that there's less boilerplate code needed for data management in UI. Also a gross oversimplification as to what Compose is. But yeah, the code you see here, we have this composable, and one of the interesting things is that when you see this annotation, it's not recognized as an annotation. This annotation will change the underlying behavior in the compiler, and now it will recognize the entire thing as a composable like UI. So this is not actually an annotation in a function, it's now a view. Okay, Jossie Wolf and I gave a few talks on Hitchhiker's Guide to Jetpack Compose at a couple DroidCons last year, which is well worth watching if you want to understand the internals for Compose. But we're gonna just take like a super small snippet from some of this, since this is like the touching point. Compose uses slot tables to automatically assess at runtime whether the state of certain views have been dirtied. When the slot table is filled up, it holds all the objects from composition and the entire tree in execution order. The slot table changes values by range. We can change the group, states, and the UI that accompanies it. And when that value changes, it can trigger recomposition, as it does when there's like a generated bit mask value that changes at the runtime side. Okay, so we kind of understand, all right, so we have these composables, and then once like the code compiles at runtime, there's this like self-managed memory that's kind of doing a lot of that work for us. We're looking at this code example again, only now we're gonna see how this is accomplished, because this is accomplished through IR transformations. This is the human-readable version of the generated IR code for the Hello World example. It's a lot of text, so we'll break it down. Okay, so we have that original greeting that we saw in the original code, but then you'll notice that there are a couple other injected parameters at the IR level. So composer is injected, and it forwards every composable call, so composer is available for every subtree, and it keeps track of the groups in the slot table. The changed parameter comes from the generated metadata values to check if the input has changed since the previous recomposition. It enables the ability to skip recomposition. And yeah, so this is like kind of the small portion of code that we're really going to look into when we start digging in the compiler, but we'll go ahead and just kind of explain some of this other stuff too. Compose also generates some low-level bit math to determine if the changed bit mask is dirtied. So if it is, recompose occurs, and if not, then we skip. I already kind of gave away that we're looking at the IR phase, so no surprises there. But we can confirm to check which components have been extended and registered, and we can see that it is indeed the IR generation extension. Interestingly, there aren't really any contracts for IR, so I thought it was kind of fun to spot this, the whole bit about the validate IR, verify that our transformations didn't break something. So yeah, you can do a lot with IR, but it is important to check and make sure that what you're doing isn't going to break everything later on. So that was just kind of a fun spot. Okay, wait, I think I lost my spot a little bit. Oh yeah, okay, so we're going more into the code, and we see that there's like kind of a composable symbol remapper. The symbol remapper is aware of possible descriptor signature changes to which aligns with the function signature and the descriptor signature in the cases of composables and value parameters. And also, it removes descriptors whenever signature changes, forcing it to be generated from IR. So there's like an example here where it's like the fun A at composable, and it takes it takes a composable function as a parameter, and then it might change to fun A, and then there's kind of like two of those. Okay, whoop, I lost my spot again. We're at the composable symbol remapper. Okay, we're following through with all this, and we have the composer param transformer. This is responsible for transforming all the composable functions to have an extra synthetic composer parameter. And I think that's kind of where we want to keep going from there. Yes. Okay, so yeah, we have the composer param transformer. We go to that file, and we can see here that this is the logic responsible for changing the IR to input the change. So this is the portion of the code that puts in the change parameter in the IR itself. It takes, it kind of just like loops through, and you'll see that there's this changed param count, which takes in the real value params, and then also the param count, which I feel like I lost my spot. Oh yeah, so if we click in, this takes us to another file, composable functions body transformers, and we have the change param count, which calculates the number of change params needed. And so there's like a little bit of extra math going on in here, and then it also makes use of the extension function for this param count. One thing that I found surprising about all this code, this is sitting in the Android Xcode, and this is an external plugin, but I did find that a lot of this IR code was pretty readable in comparison to some of the older versions that I've seen. So I was pretty surprised to see, like, okay, like you can kind of just figure it out. It's a whole lot of poke and prod. Nothing fancy. So now that we've looked into some code, not too much, just a little bit, and we looked into that, but now we're going to go back to our composable example, and we talked about the human-readable version of what it looks like for IR. Now we're going to look at what it actually looks like, and this is what it actually looks like. I'm a little disappointed because I feel like all my highlights are gone. I'm like, where are all the highlights? That's why I was like, where? It would have been nice if you saw the highlights, because then you can like really tell what the differences are. Obviously, we can see one side is super blown up. This is personally the first use case that I've seen where IR transformations are just super blown up. You're supposed to really just simplify stuff, or at least that was the original purpose. But yeah, this is literally, this is how Compose manages this memory for UI state at runtime. And this will either change the way that we look at writing plugins, or we're going to learn some really good lessons down the road. Either way, I can't wait to see which way it goes. Okay, what now? Well, we exchange notes. I wrote an article a year ago on the first part of the Kotlin compiler, so that is on Medium. I know a lot of people have been waiting on the second part. I assure you, it is in the works. It got kind of torn up. I ran out of time, then I had to write this talk, but very soon after this talk, I'm sure this part will be published, so definitely keep an eye out for that. There's also a fun little GitHub repo. A lot of it is scratch notes. It's called Kotlin Compiler Crash Course. And there are also some super helpful notes on debugging points, testing points, and instructions for setting up the Kotlin compiler, Compose, and more. And I think there are also references of all the talks that I've mentioned in this talk, so you can also check out those links there. I'll give it a few minutes so people can take photos. We good? Okay. And here's my one shameless plug. If you like my work, or if you're into Android, or if you're into Kotlin and coroutines and want to learn about coroutines in general or structured concurrency, you can show support by checking out Programming Android with Kotlin, Achieving Structured Concurrency with Coroutines. I believe we also have books for giveaway. I know they're up at the front. I don't know how we're going to do it yet, so I'll figure it out. But there are books that will be available for giveaway. So I don't know. I'm sorry. Maybe I'll tweet something out once I figure out what we're doing. Yeah, thank you so much. We're just about at 11:45, but if there is time for questions, oh, there is time for questions. Yeah, what questions do you have for me? Oh, thank you.
Hi.
Hi.
Thank you very much. Really interesting talk. I was thinking of the Compose compiler. Whenever you have the builder, the set content, is it just another function that just has the composer injected, or has it any different signature or some magic for it?
You're asking, okay, so like with the Kotlin compiler, like we have the Jetpack Compose stuff, and you're asking if, like, sorry, which is the part specifically? Like, are you asking about the injected parameters?
Yeah, the builder to enter the composable world, if we can, if you give them the license, does it have any magic in terms of injecting this context, or is it just the same as you saw for other, as you showed for other composable functions?
Oh, okay, I hear what you're saying. Yeah, I didn't get into this too much, but what actually happens with the Compose compiler plugin, we only looked at the backends stuff, but the Compose compiler plugin actually touches just about every phase. But I believe the backend IR transformations and the resolution, we didn't cover resolution. There's a good chance, actually for the injected plugins, like that does happen at the IR level. But yeah, like there are like various changes like done. So usually at the resolution level, I think that's where the composable types are specifically created. So you have that dictionary of types that you work with, and then after, at least for the injected parameters for the composer, like that comes from the definition of the created composer type. But then the bit mask bit, like all that is sitting in the IR level. Does that answer?
Yeah.
Oh, okay, good.
Thank you very much.
Yeah.
Hi, thanks for
It
the
has a
talk. That
bookmark.
was great. I have a question. How do different compiler plugins cooperate with each other? So let's say we have two evil Sam plugins who both want to change it, but to a different place. What happens then?
I don't know if it's possible that all hell can break loose. It's super ideal to write testing around this stuff. I mean, generally, a lot of the plugins do work well together. I think if you keep your plugins kind of small, the risk is a little bit lower. I do know, like, let's think about Compose, for example. With like Android development, there's a lot of like those crossover libraries, and even like not even just like clashing plugins, but it's more like, okay, there are some changes here, but now it's like some libraries needed to have like a little extra work done. Like I think there's like a hilt crossover just to make it work. So yeah, I think actually looking at Compose and all of the subsequent libraries that kind of like came from that is kind of a good example of if you write a plugin, like depending on how far you derive from the original behavior or not, like yeah, there's a chance that that stuff can really clash and make things kind of difficult. So
Okay,
yeah,
thanks.
I think there's a question up here.
Hey, so long time ago, I experimented writing a plugin for IntelliJ, and I ran into a lot of the same stuff with the PSI and stuff. And I was wondering, where does IntelliJ start? Where does the Android compiler stop? Which things are overlapping, and which is reusing stuff from the other, or are they completely different things?
That's a really good question. This talk was dense, so I had to keep the scope so small. But the interesting thing is that IntelliJ is like technically like the whole like Kotlin source code, like anything related to IntelliJ, it's all just kind of in the same source code. When it comes to the compiler logic itself and like how it relates to IntelliJ and how that works, if we go back, let's see, we're so far, oh my gosh. That's all right, we just need one of these. Yeah, if we go to the FIR stage, so we make it to the end of the front end of the compiler, and at this point, you have like your checkers and your diagnostics, so you have all the information that you need. Oftentimes, like this is the information that you need to be able to send it to. We talked about compiler plugins for this talk, but then there are also IDE plugins. That is a whole other thing. And there are some differences. I haven't studied IDE plugins as much, But I do know, like, for example, when you're working with PSI and you're sending it off to the IDE plugin, it's interesting because, you know, we talked about descriptors for this talk, which has a lot of information, but then there's this idea of synthetic descriptors. So it's just way less, you have way less to work with, and that is what is sent over for information to use in IDE plugins. So a lot of it is kind of related. I would say, like, the way I kind of look at it is like, if we're going to talk about IDE plugins, it kind of splits off right after the front end. So everything, when you're working with the IDE plugins, like everything you need is in the front end, and that's why we're able to run things a lot faster nowadays with all those FIR changes.
Thanks.
Oh, yes, and also if there are JetBrains people in here, if I was wrong about anything, you can definitely just put it in the comments in the YouTube thing. And also, I do appreciate all the help that was given for this talk. Yeah, just a little tidbit. Are there any other questions? We might have a little bit more time.
So I don't know too much about security, so this might be a dumb question, but is
There are no dumb questions.
is there anything that is possible if you were to write a malicious like plugin at the compiler stage that would be much harder to catch? And are there any security checks against that the compiler does at various stages?
Yes to the first one. I don't know to the second one. Theoretically, yeah, see, that's the thing about this talk. Like, there are a lot of implications for this talk, and it's not a dumb question. I see you're already seeing the implications of understanding, like, what working with compilers can do. Yes, theoretically, you could do that. And I don't know if there are security checks. What I would say is, at least for, like, we can go back to the compose bit with the IR transformations. I mean, I guess if you wrote a plugin where it's like, yeah, I'm going to do some security attacks, and it's not going to actually intercept anything, we're just going to maybe within the IR, like, have a little runtime thing. Yeah, I guess as long as everything is working, like, you could potentially do that. What I do know is if you have something that causes it to break later on, like, that could also be kind of bad. So I guess it's whatever. I don't know. I feel like this talk is now just kind of unleashing chaotic ideas. But hey, no one told me to stop sharing it, so here, you know. Yeah, I don't know if there are security checks for that sort of thing, but it does bring up some interesting thoughts and discussions for that afterwards. Okay, it's 11:52. I don't know how much, like 5 minutes? Okay, maybe like 2 more questions, and I'll like step outside if anyone wants to take it outside.
Hi, I'm here.
Oh,
Nice talk, by the way. Thank you very much. I'm not
you.
familiar that much with like compiler plugins, so this might be a very basic question. So what I'm interested in is, do you have a good process of testing and debugging this stuff? Because I imagine once you start writing code and also the compiler parts for it, maybe code generation and stuff like that,
Yeah.
then it can be harder to spot bugs in your code. So I imagine you also write tests for the compiler
Yes.
plugin, but also for your code, and then how
Yes.
this blends and how you can find where the bug actually comes from.
Yeah, no, that is not a basic question. It's a very good question, too. These are all great questions. No more self-deprecation. Yeah, so testing is the way to learn everything about compilers. So that is one nice thing about the Kotlin source code. They have a lot of testing set up in the GitHub repository. There are instructions around that, so I did mention that briefly. But let's talk about like what that actually is, because sure, there's like tests for regular stuff, but testing for compilers is different because you have to create your own like semi-mini configuration compiler, like a simpler version of it. So yeah, there's like all this setup around being able to run tests, and then Depending on what kind of test you have, like there's the FIR facade analyzer, and then there's also ones around. There's tests for like every level, but let's talk about the FIR one. So you might have like a set of test data, and you like run through the tests, and it'll set up this like semi-compiler, and it will generate the code and then output that text afterwards. So there's like a couple Gradle commands you have to run to be able to do that. And this is largely how I was able to like literally, you can literally do all this and then input your own text files just to play around and like see how this works for you. So yeah, I do know that also like some folks have been playing around with compiler plugins. I can't remember the name, but there are some popular like little tiny libraries on helping to set up with like a compiler plugin related tests. And yeah, that would be definitely the area to look at. And it is different from regular JUnit testing. Yeah.
Thank you. And is there like some kind of debugging tool around this, or?
Yeah, you can still debug the code.
Okay.
Yeah, like regular, once you have that like strange little test set up. You can still debug it like normal.
Thank you very much.
Yeah. Yes, these are all good questions. Yeah, I have time for one more.
Hi. So my question is also about debuggability. So let's say we're generating some code, right? So now your function has a bunch more, like in the compose example. When you're debugging, you see your source code. It doesn't have all that added code, right? So how do you actually manage the mapping? And is that something you have to do manually? Or can you just rely on the Kotlin compiler to know exactly where you need to set your breakpoints and stop and continue?
Okay, so the question was, it's around debugging, and it's around which mapping part specifically? Just the data transformation mappings or the type mappings? Or like PSI and descriptor and the IR mappings?
At the IR mappings level, yeah.
Well, honestly, that depends on the kind of code that you write. But yeah, let's go to the composable bit. So I mentioned that there were multiple phases that it actually touches. So, you know, when it comes to the IR transformations, you are responsible for creating those extra symbols. And it is, I didn't check this one particular well, actually, I think it might have been in the code where we kind of end up remapping some of the definitions, so you are also responsible for doing that. So if you create a whole new type in Kotlin, you probably need to do some subsequent like mappings to make sure that the Kotlin compiler knows what to do with it. Yeah.
Okay, thank you.
Yeah. We have 3 minutes left. And I don't know. I guess we'll just like cut it here so that the next person has time, but I can just step outside. And yeah, thank you so much for your attention and your time, and thank you for coming to the talk.